No, great. So now it is my pleasure to introduce the last talk of the first parallel session of the day. And I'm going to introduce now Péter Vrana from the Budapest University of Technology and Economics, who is going to talk about the semiring of dichotomies and asymptotic relative submajorization. So please, Peter.
Thank you. So as the title says, we're going to talk about three things: the semiring, dichotomies, and asymptotic relative submajorization. I'll start with the dichotomies first, and then introduce the problem in terms of this asymptotic relative submajorization, and then the semiring part will only enter the proof. So, okay, well, sorry. So by a dichotomy, I mean a pair of quantum states on a common Hilbert space. So one thing to think of is that, so that there can be two interpretations of such a pair of states. One of them is that you imagine a black box that is prepared in one out of two possible ways, either described by the state rho or the state sigma. And another interpretation is that you have a state rho and sigma serves as some sort of reference. This will be clear a bit later. And the second ingredient is about transformations of such pairs of states. So I took one pair rho1 sigma 1 on some Hilbert space, and the channel which goes from this Hilbert space to another one. And I'll say that this channel T transforms the pair rho1 sigma 1 to rho2 sigma 2 if T of rho1 is rho2 and T of sigma 1 is equal to sigma 2. It's worth noting that since these channels are in fact linear maps, we can, and it is sometimes convenient to allow states or not states, operators with trace different from one, because you can rescale both sides. So if you say that the state rho1 gets mapped to rho2 is the same as saying that the positive operator C times rho1 gets mapped to C times rho2 for any non-zero constant C, which will be positive. So one example where such a relation pops up is majorization. We have a pair of non-negative vectors, say probability distributions P1 and P2, and we say that P1 majorizes P2 if, when you order these entries of the distributions in a decreasing way, then the sum of the largest k ones for the first distribution is always greater than the sum of the largest k probabilities for the second one, except of course for the last one where you have equality. So this can be this problem can be embedded in terms of our notions. So we'd say diagonal density matrices. We put the probability distributions in the diagonals of these matrices rho1 and rho2, and all the off-diagonal elements are 0. And I choose sigma 1 and sigma 2. Remember, this is what the reference state was, to be the identity matrix. And this is already an example where you can see that it's not normalized anymore. Right, and as it happens, this probability vector P1 majorizes P2 if and only if you can transform the pair rho1 identity to rho2 identity in the above sense. And another way to say it is that there's a doubly stochastic matrix that sends your distribution P1 to P2. And this majorization relation is known to have many applications in quantum information theory. So one way to think of it is that it captures that one distribution is more mixed than another one, but it also enters in the condition by Nielsen on transformations between pure bipartite entanglement states under LOCC, so local operations of classical communication, also in the resource theory of coherence. Another example is the class of Gibbs preserving maps, which is related to the thermal operations. So thermal operations are some model of an interaction of a system with a heat path at a certain temperature given by this inverse temperature beta. And one feature of thermal operations is that they're Gibbs preserving maps. So a map is Gibbs preserving, it preserves the Gibbs state. So there's some Hamiltonian and this inverse temperature beta. And then again, I make use of this rescaling property there, and I do not normalize the Gibbs state because it's not necessary. Right, so the condition for being Gibbs preserving or existence of a Gibbs preserving map spanning row 1 to row 2 is that this pair gets transformed to this other pair by T. Right, so as I said, the thermal operations are examples of Gibbs preserving maps, and in fact, classically, it is the same to ask that the row 1 can be transformed to row 2 by a Gibbs preserving map or a thermal operation. The third scenario where these notions are useful is in hypothesis testing. More specifically, in a binary hypothesis testing problem, you're given a black box that either contains rho or sigma, and you would like to decide which one is the case by performing a two-outcome measurement on the system. So this two-outcome measurement is in this diagram represented by the pair pi and identity minus pi, or pi is some operator between 0 and the identity. And then the interpretation that of the application of a map to the pair rho and sigma is that you're given this black box and then you apply some physical process, then you end up with a different black box that either contains now T of rho or T of sigma. And in this hypothesis testing scenario, you can say that the latter is less distinguishable than the former one, because whatever measurement you can perform on this transformed pair, you can also do a transformed measurement on the original pair. Right, so one modification of this notion of joint transformability of a pair of states is called a relative submajorization. And in a nutshell, what you do is relax some of the equalities to inequalities. So first of all, your states need no longer be normalized, and then the traces will be interpreted as success probabilities or probabilities of the transformation to succeed. And in addition, you would allow your channels to be unnormalized or subnormalized, namely traced and decreasing maps. And then you do not want to transform row 1 to row 2 exactly, but only to something that's larger than row 2. And you require a reverse inequality in the second component. So as you can see, the role of the two states is no longer symmetric. So this relation is called relative submajorization. I will use this kind of curly less than or equal sign to denote that. So this means that there exists a trace non-increasing positive map T such that T of rho 1 is at least rho 2 and T of sigma 1 is at most sigma 2. Right, so this should be interpreted as some certain kind of probabilistic transformations, but also there's a way to encode certain approximate transformations in this formalism. So why would that relaxation be useful? So one of the examples was hypothesis testing, where you perform some two-outcome measurement on the state, which is either rho or sigma, given by this POVM, which is now just a pair of positive operators summing to 1, the identity. And then the probabilities of the outcomes will be the trace rho pi and trace rho times identity minus pi. But since rho was normalized, these probabilities sum to 1. And in principle, there's no need to keep track of both outcomes. There's a redundancy in this description, which can be eliminated by focusing on one of the outcomes. So let us call a test a completely positive trace and increasing map, which is of this form. So I simply take the trace of rho times pi for one of these measurement operators, the PUVM elements. So as you can see, this will be equal to the probability of obtaining the outcome associated with pi, which is some number between 0 and 1. So more precisely, now if you consider a test, so this is maybe it's good to point out at this point that this is the most general form of of a completely positive trace line increasing map from this Hilbert space to a one-dimensional Hilbert space. And this allows us to characterize the possible errors in this this hypothesis testing problem, state discrimination problem. Namely, the pair rho and sigma is bigger with respect to relative submajorization than the pair AB, where A and B are now numbers between 0 and 1. If and only if there's a test for which the so-called type 1 error, which is the error that you get when the real state is rho, but you declare, you conclude from your measurement that it was actually sigma, is at most 1 minus A, and the type 2 error, which is the reverse scenario, is at most B. So this gives a way to control both types of error in a single relation. There will be an operation which is interesting to us, namely the tensor product. When you take two pairs of states or dichotomies, then you can take the component-wise tensor product. So the product of rho 1 sigma 1 and the pair rho 1 rho 2 sigma 2 will be the pair rho 1 tensor rho 2 comma sigma 1 tensor sigma 2, which will be a dichotomy on the tensor product Hilbert space, so a larger one. So one example where this is useful is that if you take two systems with some Hamiltonians H1 and H2 prepared in some states rho 1 and rho 2, then the corresponding pair we called it in this Gibbs preserving setting was rho 1 and the Gibbs state, or the unnormalized Gibbs state. Maybe it's better to normalize actually in this case. It's not strictly necessary. So it will be described by these two pairs. What do we get if we take the tensor product of these? If we take the total Hamiltonian for the joint system to be H1 tensor identity plus identity tensor H2, which means there's no interaction between the two parts of the system, then the Gibbs state will factorize in precisely the way that is governed by this tensor product. That should be H2. Right, so if the systems are prepared independently, so there's a tensor product structure on the states, and there's no interaction, then you get this type of product where, again, this should be H2. In the other example, you might be interested in asymptotic hypothesis testing, where you're not given a single copy of your state rho or sigma, but you have access to many copies of them, and you wish to perform a joint test. Joint measurements on those. Then you can still define these errors for the tensor product. So you now wish to discriminate n copies of rho from n copies of sigma with some joint test. And you might be interested in the asymptotic behavior of these two kinds of errors. For example, the quantum Stein's dilemma says that you can have an asymptotically vanishing type 1 error as long as the type 2 error does not decrease too fast. Namely, the decrease should be at most exponential with an exponent given by the relative entropy between the two states. And going beyond the Stein lemma setting, you might ask what happens if I demand the type 2 error to go to 0 faster than what is allowed by the Stein lemma. And it turns out that the type 1 error will go to 1 instead. So previously it was going to 0, now it goes to 1. And it does so exponentially. And the optimal exponent, so you want to, and in this case, you want the exponent to be as low as possible so that the convergence to 1 is as low as possible. And the optimal, this error exponent is given by this supremum over some formula involving the sandwiched Renyi divergence between the two states. Right, so a natural generalization of this setting is what I call asymptotic relative submajorization. So similarly to this asymptotic hypothesis testing problem, we wish to compare many copies of of our initial pair ρ1 sigma 2 and many copies of our target pair ρ2 sigma 2, where I added these exponential factors. So we might be interested in the trade-off between the two kinds of exponents. Right. So as you can see, the special case is what we've seen before. If these states, ρ2 and sigma 2, are both trivial states and then a one-dimensional Hilbert space, or in fact on any Hilbert space, if the two states are the same, then we get back this strong converse problem. Right, and the way we compare these is by relative submajorization. It should be right that even though this relative submajorization was defined in terms of an inequality for both the first and the second components, in fact, in the second component, this can be made exact. So without loss of generality, we can even require the transformation to be exact in the second component. Yep, so as I said, our goal is to characterize a trade-off between the two kinds of exponents. And our result is precisely this. So suppose we have these pairs ρ1 sigma 1 and ρ2 sigma 2. There's some support condition which they must satisfy, that the support of ρ is always within the support of sigma. And then given these exponents r and capital R and little r, this relative submajorization holds asymptotically if this rate is bigger than a certain threshold, which is given by a similar formula as before. Right, so this is what the sandwich ring divergence is. Let me say a few words about how the proof goes. So this is where the semiring part will appear. So in general, when you wish to decide such a relation, then there are two natural approaches to do that. So one thing is that by definition, if you succeed to find the channels which carry out these transformations, then you might say that you have found a construction, and then you get some bound that these can be compared asymptotically. Whereas if you wish to disprove that they can be compared asymptotically, then a different strategy is required. Namely, you typically look for monotone quantities, so some quantity which evaluates the number on the first pair and then the second pair, and for some reason you know that it should not increase under such a transformation, but numerically you find that its value on ρ2 sigma 2 is bigger than on ρ1 sigma 1. So then you have an obstruction which prevents this relation from holding. So what we do is a bit different. Namely, we will not consider any constructions at all, but instead we have a proof strategy which is two steps. We first show that the special class of obstructions in fact suffice. So whenever this relation does not hold, there is a certain type of obstruction which shows that. And then having some implicit description of these kinds of special obstructions, we then go on to classify them and then find out what they are. And this leads to this preordered semiring setting, which is probably not so familiar to many of you. So let me just say that the preordered semiring is some structure which is a bit like the natural numbers. So you have an addition and a multiplication. There's a 0 and a 1 element, which are units for these two operations. They satisfy all those axioms that you would expect. So they are associative and commutative, and they distribute. And in addition, you have this preorder relation, which is like a transitive and reflexive relation. You can also think of partial order if you like. It doesn't really change the point. And there is a compatibility relation between the two. Namely, you can add inequalities and you can multiply inequalities. So one of the consequences of this one is that everything is bigger than 0. Right? So in addition, you require the preorder to be the usual one on the natural numbers which sit in S. And in this setting, you can already define something called the asymptotic preorder in general for a suitable element, assuming such an element exists. I'm not going to go into details. You define X to be asymptotically larger than Y if the powers of X are larger than powers of N up to some sublinear power of your element U. So what kind of abstractions should one have in mind? If you take now a function from S to the non-negative reals that is multiplicative and monotone with respect to this relation, then it will also be monotone with respect to the asymptotic preorder. That's not difficult to see. So we will in fact require something stronger about our abstractions. Namely, we define the spectrum of this preordered semiring as a set of homomorphisms into the non-negative reals that are monotone. So previously, to get an abstraction, I only required F to be multiplicative, but now I also require compatibility with addition. It's a stronger condition. So as we saw before, this is a stronger condition. We still have this implication that whenever X is asymptotically bigger than Y, then for every element in the spectrum, you have the right ordering. The surprising thing is that in certain circumstances, a converse property, a converse relation also holds. So if this preordered semiring satisfies some additional conditions, then in fact, X being asymptotically larger is equivalent to F of X being larger than F of Y for every element in this spectrum. Right, so this is how we implicitly define the class of relevant abstractions. Yeah, here are some examples of preordered semirings that have been studied before. I'm not going to go into any details. I just want to point out that there's a diverse set of problems that seem to be possible to handle with this kind of machinery. And the other thing I would like to point out is that there's this kind of dual characterization, which these two theorems allow. And so this theorem by Strassen is a more restrictive one, and there's a generalization which works under weaker assumptions. And the problem we are looking at requires these weaker assumptions. So how do we translate our problem to this preordered semiring setting? We take these dichotomies and more precisely equivalence classes of pairs of positive operators subject to the support condition. We equip the set with the operations induced by the direct sum, which is like putting these matrices into block diagonal matrix, and the tensor product mentioned before. And the preorder is relative submajorization. So after showing that it falls under the class of semirings where we have this dual characterization, we need to classify elements of the spectrum. So in detail, what that means is that we are looking for functions defined on pairs of positive operations subject to this support condition that are multiplicative, in this sense, additive in this direct sum sense. So these are the block diagonal matrices, normalized when we plug the identity matrix of size n to both entries and get n, and it has to be monotone, which can be replaced by these two conditions. That first, I require monotonicity with traced and increasing completely positive maps. And in the second step, you might recall that we are allowed to increase the second component and decrease the second component for free. This gives some additional conditions on the monotonicity. Right, and what turns out is that these properties characterize basically the sandwiched Renyi divergences up to the logarithm and the alpha minus 1 factor. At least in the parameter range with alpha bigger than 1. So let me conclude with a summary. So what we have is a characterization of asymptotic relative submajorization in terms of sandwich Renyi divergences. And at the same time, we extend the operational interpretation of set divergences and find a new axiomatic characterization of them. On a more conceptual level, what we used as a new technique for studying resource theories. When I say resource theories, I mean in a very abstract sense. We can study them directly in the asymptotic regime. So we cannot say anything about finite n transformations with these tools. And as I may have convinced you, these tools can be applied to many other problems like zero communication and LOCC transformations of pure states. So I would be happy to see any other applications you might have in mind or suggest. And maybe one interesting question would be to extend these methods to different asymptotic regimes, which is at the moment not clear how to do. Okay, I'm not sure if I'm over time yet, but that's basically the end of my talk.
Well, thank you so much, Peter, for the very nice talk. I really enjoyed it. I was thinking that since we started, I mean, we are finishing the talk a bit late because we started it a bit late. Maybe it makes more sense to directly forward the discussion to the roundtable since it was supposed to start this time anyway. Okay, so I guess then I leave you to join your roundtable, and all the participants are also welcome to join you there and follow the discussion there. So thank you very much again for your talk.